This example comes from section 6.2, Sum Difference in Double Angle Identity. I'll start off this one by asking, what does sine of 90 degrees plus 60 degrees equal? Now, 90 plus 60 is a nice number, so I really realistically would solve this problem as with sine of 150 degrees, which if I know my unit circle reasonably well, I can figure that one out. Even a calculator will tell me that that one equals a half. Now, one common mistake that students make is they think that sine of 90 plus 60 should be the same thing as sine of 90 plus sine of 60. Now, if you try those two separately, sine of 90 equals 1, sine of 60 is root 3 over 2. And if you add those together, they definitely don't equal a half. So you do find that these are actually not equal to each other. So not exactly a proof or verification. In fact, we found something that wasn't true. Turns out we have an identity for what does sine a plus b equal to. You'll find it on your identity sheet under the trigonometry section. It says that sine a plus b equals sine a cos b plus cos a sine b. So how would that work in this case? Well, we already know that sine of 90 degrees plus 60 degrees is equal to sine of 150 degrees, which equals a half. But let's take a look and see if it actually does equal sine of 90 times cosine of 60 plus cosine of 90 times sine of 60. Not necessarily to prove it, but at least to verify in our own minds that it does seem to work. We have sine of 90, which is 1, cos of 60, which is a half. Cos of 90 is 0. Sine of 60 doesn't really matter now since that's 0, but we do end up with 1 times a half plus 0, which equals a half. We get the left side equal to the right side, so we've at least verified that the identity works. So let's write down a couple more of these. So you have a sum identity for both cosine and tangent as well. Notice that they do look different from the sine one. I don't expect you to start trying to memorize these. You're going to get that formula sheet for every test and quiz you write. So the cos a plus b identity is surprising in that there's a minus in it. The tan a plus b one is even worse in that there's a fraction, a plus on top, a minus on the bottom. But as long as you can execute the questions you'll be asked about them, you don't need to know them off by heart at all. So I'll write down also the difference identities for sine, cos, and tan. You'll notice that they do look a lot like their respective sum identities, with basically just the signs switched in all situations. There's also a double angle identity for sine, cos, and tan, so I'll start by writing those down. And we have these three. Sine 2a equals 2 sine a cos a, cos 2a equals cos squared a minus sine squared a, and tan 2a equals 2 tan a over 1 minus tan squared a, all of which you could have gotten by just saying a plus a in the identities up above, the sum identities, and you could have come up with these ones. Also true that if you look at the cosine 2a identity on your formula sheet, you actually have three different forms of it. They've basically used the fact that we know that sine squared plus cos squared equals 1. To replace cos squared with 1 minus sine squared in one case, and sine squared equals 1 minus cos squared in the other case. Truth is, you don't need to be able to derive them anyway, because you get them again on your formula sheet. So 2 cos squared a minus 1 is useful, and 1 minus 2 sine squared a is useful depending on what the situation is. So all three of those are identities for the double angle for cosine. So in the next example, we'll see maybe some more uses of these besides just having a huge list of formulas on a sheet.